some data, time versus temp, and we had these points, and we have to put them on to our graph now, okay? And so someone said we took the data, and then someone said, why don't we plot it up? Because our goal is to get a mathematical model here. The first thing is, what's our first point that we have? 0, 5.2. So I could take this 1 and put it down around 5.2 and 0 there. See, I did that? The next one we have is 0.5, 7.4. Okay? So, uh-oh. Why do I have it marked like that? Did I do that? And you didn't tell me anything? These are also some we moved back. Now that's not the origin. That's 0, 5, but it still should be, I shouldn't put 0 over. So that was off a little bit, I'm sorry. I didn't even realize it. 0.5, 7.4. So we've all plotted up data before, so that's no big deal. 1, 9.3. 1.5, 11.1. 2, 13.5. Bless you. And 2.5, 15.9. What do you notice about the data? A fairly amount of straight line, although there might be some upward trend. We could be going into the afternoon hours. So we're going to model it with a straight line, but realize that the straight line might not be the best actual model for what would continue, especially if we go into the night and it starts going back down. Right? So you take a ruler and you stick your ruler on your data, and then you draw your line, okay? So I'm going to draw the line in. Something like that, okay? And I'm going to get rid of this. Now, you could draw probably a little straighter line yourself because you have a nice ruler. But now, when you look at that, does it go through every point exactly? No, if it did, it would be like that. It would be like a stair step, or some weird sort of thing. Now, so that's not how it is. Our goal isn't to get it through every data point. It's just that it gets close to each one. So that's called our best fit line. We've all seen that. Now, what can we do with a best fit line? Spencer. We can, okay. That's true. We can approximate values down on the table. And to be able to do the approximation of the values that are not on the table, that are actually interpolating data with our graph, we call that. But to be able to do it more exact without just estimating from the graph, what would you do now? Michael? We can make an equation, right? And we know the equation of a line. The equation of a line is just what? Y equals mx plus b, right? Has everybody seen that? What is m, Vera? It's the slope. So we have to find slope, and slope is change in y over change in x, or we can use y2 minus y1 over x2 minus x1, right? Now, if you look at your points on here, which red dot should I use to find my slope? It might be a trick question. Yes. Julia. The first and the last. Well, it probably wouldn't be bad, but I don't want you choosing points on the actual data points. So I want you to take points on the what? I should have made it more dramatic, but I made it up. So on the line. So let's take this point right here around 7, and let's take another one at 13 right there, okay? Now, the reason for that is because if you took like these 2 points, your line would go up like that, wouldn't it? If you took, those might be close, but this one, those 2 would be, see, so you don't want to take 2 points that's your data to make your line. You want to take 2 points that are exactly on the line, okay? So what is this point right here? Well, I have to estimate it, and you might be able to estimate it better, but it's about 1.513. And this point right here is about 0.4, 7. So I chose 13 and 7, but the other ones I'm reading off, right? Now I'm ready to write the equation of my line. What's my y2, Tyler? Yeah, 13. What's my y1, Mary? 7. What's my x2, Emma? What's my x1, Mr. Brinson? 0.4. Okay? So that gives 13 minus 7 is 6. 1.5 minus 0.4 is 1.1. 6 divided by 1.1 is 5.45, or we'll just round it to 5.5. What does that tell us? Kendra? For every hour. Because the units, what is the units of y? Degrees Celsius, right? What are our units of x? I don't know why I don't have it on here. Oh, yes, I do. Time, hours, right? So 5.5 degrees Celsius per hour is our slope. Now, what do we call, the other thing in here is b, and what is b? The y-intercept. What does our y-intercept look like here? Well, no, remember it's the y value, and this isn't actually the origin. It's about 5, right? So b equals 5. Well, 5 what? 5 degrees Celsius. So putting this all together, we have y equals mx plus b, okay? Y is our temperature, right? M is 5.5 degrees Celsius per hour. X is time, we'll call that little t, plus b, which is 5 degrees Celsius. And this is our mathematical model for our data. Starting at a temperature of 5 degrees Celsius, we'll expect our water to raise its temperature 5.5 degrees Celsius for every hour. It's quite an intense sun, but I just made up the data, so that's why it's like that. What? Yes. So now comes the question. Big T is temperature, little t is time. Okay? Now, someone mentioned, Spencer, I think, about interpolating. You guys don't need to bring these to class. okay? So you don't have to lug this around. This is more to do your chapter blocks at home and stuff, okay? Was this yours? If so, I'll tell you. Yeah. Well, because like in early October, I go out for a conference, so I might tell you bring your book in to work on your chapter blocks. Okay? So let's do some interpolation within our data. So that means, well, what might be the temperature? So we could say, what is the T at time equals 1.25 hours from start? Okay? 1.25 hours from start. Well, we would just plug it into our model. 5.5 degrees Celsius per hour times the time, which now is 1.25 hours, plus 5 degrees Celsius. Now, what's 5.5 times 1.25? It is 6.875. We'll just say 6.9. Now the hours cancel, so that leaves you what? Oh, that's good, because it's going to have to add to this 5 degrees Celsius. And you can only add them if they're like units, right? You can't add degrees Celsius plus toenails or something. 6.9 plus 5 is 11.9 degrees Celsius. So we could see that at 1.25 hours would be about 11.9 degrees Celsius. That's interpolation, because we're within the data. We interpolated. Well, what is extrapolation? What does that mean? Carolyn? Who knows what extrapolation means? Julia? Outside of our range, to extrapolate it out, to go farther beyond. So what's a time beyond what we have here? Spencer? 10 hours. Okay. So we could use our model to see what our temperature would be to come up. Our model is what's telling us what our temperature doesn't mean that our model is right out there, right? At a time of equal to 10 hours. So T equals 5.5 degrees Celsius per hour times 10 hours plus 5 degrees Celsius. So the hours cancel, and we get 55 degrees Celsius plus 5 degrees Celsius. Therefore, we can logically assume that our water will have warmed up to 60 degrees Celsius in 10 hours from the time we put it out. Right. Or turn to evening, and the sun went down. That would say that our data, which is going from like, I probably put the water out, say, at 10 a.m. or something like that, and going. So it doesn't make sense. It's the danger of extrapolation. But in many things, we do extrapolate it out. In labs, starting tomorrow, we're going to extrapolate out to find how much steel cable we'll need to hold up our suspension bridge. But to do that, we're going to use ropes like this. Now the steel cables are this thick, and our ropes are thin. This is the thickest. I should go get thicker rope from somewhere. Anybody have like a 19th century schooner or something? Schooner, sailboat, a ship. If you got any thick rope, bring it in for tomorrow. We could use it. Yeah, something like that. Yeah. If you have some of that laying around in your basement, bring it in. So that we extrapolate out, but there's danger in extrapolation, right? In this case, we were able to see like 60 degrees Celsius. Does it make sense? Well, what is that? That's pretty hot. Well over 100 degrees. Well, 60 times approximately, hold on. 60 times approximately 2 is 120 plus 30 is like 150. So around 150 degrees Fahrenheit. Yes. Right. So that's sort of the point here. We can use it to model our data on that day with that sun temperature, right? But would it work the next day? Well, not if it's cloud cover and there's no rise in temperature. Then we would expect it just to basically, our water to reach ambient temperature and sit there, right? So it has to be for the situation that it's at, yes. So that's a mathematical model for some data. Let's look at a new type of model, okay? Well, it has mathematical components too. This is a demonstration. We'll just call it orange lights. Okay. There's a light bulb. Let's turn off these lights. There's 2 light bulbs over there, right? See them? I'll plug them in because last time I had a kid plug them in, well, he electrocuted himself and, then the lawyers and stuff, they get angry. We lose kids like that. We can see, what about the light bulbs? Well, they're bright. This is a 100-watt bulb. They're phasing these light bulbs out. You can't buy 100-watt light bulbs, incandescents anymore. Yeah, well, now they're going towards compact fluorescent bulbs and LEDs, or light-emitting dipole bulbs, okay? And so those bulbs use much less energy. This makes a nice little heater, but it's very inefficient. You can make... Oh, that's a good idea. Yes, that's a good point. Yeah, so some lights need the heat to be able to melt off snow and stuff like that. In this case, though, this is not a good way to heat a room. It's very inefficient. Okay. What can you say about the light bulbs? Are they the same brightness? No, they're not, right? So you could go to Tops, okay, and you can buy paraffin wax like this, you see? These pieces of paraffin wax. And you could buy pieces of tin foil, aluminum foil, in bulk. Now, aluminum used to be considered like well, when they first made it into where they could actually get aluminum out of its ore was way back, but then they hung the person who came up with it or something because they didn't want it taking away the value of their gold and stuff. And so they didn't want that person's technology to make aluminum foil to even be known. So they got rid of him. And so it was later when it came about. So it was such a, if you went to a party when it first came back again, and you got, your silverware was, your gift was an aluminum fork, you were much more excited than the person who got a measly old gold fork. But now it's so abundant you can buy rolls of it, can't you? Aluminum foil. You could take this cheap aluminum foil and your paraffin wax, right? And then you put them together, and you get yourself a little mini light detector, you see. So if I go to the smart board with this, well, let's see, where's it good? I'll just use one of the lights. So I could come up on this light here and watch what happens to the wax. One side gets lighter, right? If I flip it over, the other side's lighter. See that? Carolyn, do you see that? One side's lighter, the other side's lighter. I find that very pleasing, but I don't know. Now, I can use this as a sort of detector of light here. If I hold it at about a hand's length from this one, I could see how bright it is. Okay? And then I could come over here, and I can do it about a hand's length, and I could see, well, it's less bright. But that's not very good, right? That sort of model didn't work so well. There's different brightness is of the bulbs. Each bulb has a different brightness. This is a 40 watt bulb, that's a 100 watt bulb. If we think of the bulb coming out like this, I measured it at a hand's length away from that, right? And so say here's my hand right here. That has a certain brightness on it I can measure with my homemade light detector, right? Now, if I was to put it, notice there's an equal amount of light coming, if it's a nice dark room, and anywhere around the bulb, like that. That's a circle, believe it or not. Okay? But of course, it's not really a circle. It's a circle in 2 dimensions, but what is it in 3 dimensions? It's a sphere. So it's really like this. But I could see that on this sphere, that's right. It's an approximation. But it's like a sphere, okay? But that's a good point. If I go farther out, I have a sphere with a larger radius, don't I? Okay? What is the surface, what's the area of a circle? Pi r squared. Here, you want to make a light detector and play with it? You can do that. Now, I have some spheres here. They're not, oh, darn it, perfect spheres. I should have practiced my juggling skills. But they're okay. They're pretty close. So what we're going to do is we're going to get the surface area of a sphere. We know the area of a circle, don't we? Pi r squared, but what is a sphere? Well, some of you might know, but we're going to figure out what it is. Pi is in it somewhere. That is true. Now, what you're going to do, Maya, I'm sorry. It's Maya Nygren, you see, so I see why that gets me. Maya would be the logical choice. She's going to trace, now pay attention, Tyler and Kendra, because you're going to have the same job that she has, okay? So if I have to explain it twice, well, I might throw the orange at you or something. So she's going to trace around this thing like this and make a circle around the orange. Hopefully a little better than I did. But she's going to make another circle, and then another, and another, another, and another. Try to fit like 6 on there. Okay? Then she's going to, after she has her 6 circles, or 5, whatever it is, then she can fit on her page, she's going to pass it to Vera, and Vera's going to start peeling the orange, not in huge pieces, but relatively small pieces. And she's going to fill up one of the circles with the orange peel. And then she's going to pass it to you, Leanne, and you're going to peel the orange and see what, and fill up one, and then you pass it on to our 10th grade Marissa and keep on going, okay? Down the line until all the circles are filled. You'll do the same thing in this row. So you're the circle maker. You're a peeler, etc. Anybody want to play with a light detector? Circle maker, peeler, and then go. You can just do it amongst yourselves. There you go. It's fine. They don't need to be perfect. The circles. With the little pieces of orange peel. And then you can eat it at the end. So it's a good mid-afternoon snack. And then you can put it in the compost over here. These are those bins they're talking. Now, environmental, what's your theme for community? I just ruined that. What's your theme for community service as ninth graders? Environment, right? So if you want to have some orange, here's a piece. So if you're interested in doing something with compost, you might want to go to those eco-school meetings and stuff. Oh, the other thing I wanted to mention was, well, also a good environment project would be working on the green roof. We need to put oil, like linseed oil and stuff, on the furniture out there, put flowers or something in. Whatever you want to do is up to you. Bird feeders, raise money for bird feeders, whatever it is. That's a project you could work on with your advisory. But tomorrow, after school, it's the robot club. So some of you might be interested in joining that. So if you are, Mr. Coburn runs that. Then they're in the process of, they got a lot of money to build a whole nice new lab over in the old wrestling room. So if you're interested in that, you don't have to have like experience building robots to go. So anyone who's interested can go over and join that club tomorrow after school. Or if you can't make tomorrow, you might want to stop by and see Mr. Coburn or Mr. Hiller knows some about it as well. So you could ask either of those guys and they'll let you know. And they need a lot of different, on the robots team, you need a lot of different people to, some people are in charge of the building of it. There's other people in charge of the programming. There's other people who are good actually moving the joysticks and moving them around. There's people, so you need a lot, they need people for a variety of jobs. So if you have interest, you can do that. So we're peeling now. You should be putting your peels in a circle, and then passing it along. So the first person was supposed to make all the circles. Well, that's all right. And then the next person starts peeling, and you keep going down the line. Oh. It's about 50 minutes. Yes. Not too big pieces. See, because then when you flatten them out, they actually take up much more area than you think they do. So That's good. Now you can eat the orange. Or you could go wash it off. I'd eat it, but you know. No. I have a plum. All right, we're getting there. Let's move it along. I see you guys are masters of extending this activity as long as possible. Did you find it? Yes. All right. So, almost done back there. How many circles approximately did you fill? So about 4? How many did you? About 4. Yeah, that's all right, but you got it. How many did you guys fill? About 4. So the surface area of a sphere is what? How many circles? 4 pi r squared, and that's true. So we just took the orange to figure out we knew what the area of a circle is, but we could extend it to a sphere by peeling the orange. Let me see. So now we know what this area around our light bulb is. We know have a mathematical formula for it. It's 4 pi r squared. And now we just have to relate it to brightness, and we'll put it all together tomorrow because class is ending. So now if you want the orange, you can just rinse it off and eat it. The peels, they can go in the compost thing over here. Okay. Let me just press some.